and I am live. That is pretty cool. Today is 9th of October 2025, Thursday. Yes, today is Thursday. And with that, let's begin. Also, we will be solving. We have to back down a little bit because I was facing a lot of difficulty while solving 1600 rated questions in the CB31 sheet. And yes, the voice is also fine. That is cool. So yeah, I was facing a lot of difficulty while solving these questions. Like these questions were taking a lot of time. 1 hour, 10 minutes, 1 hour, 25 minutes. Yes, that is a lot of time to be spending on a single question. So what I have decided is we need a strategy. Uh, a strategy is very good. Earlier, the strategy was to just practice questions from TLE eliminators and read theory from the handbook. And it seems to be breaking down a little bit because I don't think 31 questions are enough here. I think I need more practice with this. And if we using our amazing extension here, see all of the questions that I've done. Here I have done 39 questions of 1400 rating and 35 questions of 1500. But if I were, and also my rating is 1400, but still if I were to give a contest, it would tell to solve the like C question, the third question in division 2. And that tells me, wait, yes, I am live. And that tells me that there is not enough practice. So I think we should do more questions at this rating. And also, not we have to sustain the quality of the questions, not the difficulty. Yes, difficulty has to be high. Here, 1500 would be high enough, but also the quality of the questions has to be good. And by quality, I don't just mean the questions have to be difficult. I mean by quality that these questions, whatever question we do, we should be able to rewrite the code afterwards, and that question should be considered completely done from our side. That is, we, yeah, we shouldn't be facing difficulty with the same question again. And I think there would be some general principles which we can like take away from a question which we have done, and that would be our focus combined with the quantity. So quantity with quality. And shit, there is a Veritasium video on this exact thing, how to become an expert, and he lists out 4 things, right? Thing number one, if I remember correctly, thing number one was a valid environment. Okay, I can mess up the order, but yeah, the 4 things, I think I have them right. Thing number one is a valid environment. That is thing number one, with the correct spelling of environment. Iornment. Environment is valid environment. And the second thing I think was repeated practice, experience, repeated experience, and then timely feedback, timely feedback. And the third thing, the last thing, fourth thing that we need to have is deliberate practice, right? Deliberate practice. So in competitive programming, the environment is valid. If you have a correct solution, it remains correct. So yes, environment is valid. We have to repeated experience. For repeated experience, we will be doing a lot more questions than we are currently doing. and timely feedback. Timely feedback means whenever we are in a question and whatever we are hypothesizing, that we can just submit the code at the moment and see if that thing is correct or not. No, and not just that, if we also get like there are editorials in questions and we can read the editorials and get more feedback. That is nice. And deliberate practice. That is when we solve hard questions, questions with which we are feeling difficulty, facing difficulty. We should take away general concepts from those questions. And yep, that is the model with which I'll be moving forward, and that is nice. Let's move forward with that. Problem sets, and we can just search. Hello, how is everything? 1400, 1400, no shit, 1500. We'll be solving questions of 1500 rating, and I'm backing up a little from 1600 because those questions were just taking a bit more time. And I think we should practice more of these questions and also, yeah, take away general principles. Let's see. Okay, food forces is messing up. Hidden knowledge of ancestors. Mhm. Okay, cool. Let's do this one. Tmux skill server and Tmux set attach TCP start update sync. Cool. And now we can do this with a stopwatch, and that would be pretty nice. Cool. Two integers a and b, and define fa as the number of positions in the decimal representation of numbers a and b where the digits are same. For example, this 0, for this 1, for this we have, okay, and what if they don't have the same number? Okay, 1, 2, 3, 2. This is same. Okay, and this one is same. Those are the only digits same. Here, this one is same, and then 3 is same, and then 4 is same. So 3. Okay. You are given two integers L and R of the same length in the decimal representation. Consider all integers between of the same length. Now task is to find the minimum value of this, the minimum value. That would be easy if, yeah, that is easy. We can just, here minimum value is 2, here minimum value is again 2, here the minimum value is 0. Yeah, 0. Wait, here minimum value is 1. Yes, minimum value is 1 here. Here minimum value, but between x has to be greater than this, so we can afford a lot of difference. So the answer only depends on the largest digit. How much spare room do we have? Here the largest digit has a lot of spare room. Yes, in this spare room we can switch, make these two different, and this would have to be same. So answer is 1 for this 7. 1, 2, 3, 4, 5, 6, 7, 7, 1. Okay, and here answer is like the digit. Yeah. Okay, so we have to look at the highest digit, I hope. Hello, you were on 1600. Is there a mistake in title? No, it is not a mistake. It is deliberate practice. The 1600 were like a bit too much. They were taking more than 1 hour. So I guess I'll practice more 1500 rating and then move on to 1600. And yes, what are the limitations? Yes, did you check out that Radev's blog, mental state blog? This one. This is pretty cool. He says that every good person gave a part of their life to CP. And I don't mean giving up Saturday parties or having no friends. I kind of mean the part of their brain. You have to really want to get better and find real pleasure in practicing and watching your progress. It also means catching yourself thinking about various problems or seeing algorithmic interpretations in many aspects of real life. So you have to kind of give a part of your mind to competitive programming. That is very nice. Like this article was pretty cool. No, yep, here it is. This article is pretty cool. Okay, yes, limitations we can use normal integers. And this, how much spare room do we have? What does that spare room depend on? How much can we tweak the value of x? It depends on the number before x. Okay, this number, the spare, the extra. Okay, let's represent for, let's say, for the ith digit here, ith, this digit. How much extra buffering do we have between these two numbers? We will start from the highest value, which is this hundreds value, and the extra number of numbers is 0. Okay, so yes, it is literally 0. Yes, 0. So yeah, this will add 1 to the answer, and we will then move on to the next number. And also, yes, we will move on to the next number only if the previous values were had a like 0 spare room or negative -1 spare room. Spare room would be -1 if the highest digits are same. In which case, we would have to add 2 to our answer. But like here, we see that the spare room is a lot, but not just that. We have to subtract the higher digit from, shit, this is the higher digit, this is the lower number. Here we do 2 minus 1. Okay, let's not represent the number of extra digits in between. Let's represent how much further apart these two digits are. This higher rated digit, this is the highest digit. These two have a distance of 1, and there is no extra digits which we can give to our x number. So we will have to choose, go with either 1 or 2, does not matter, right? And we will add 1 to our answer, and we will move on to the next digit. Here we do 0 minus 9, and shit, what do we get? 0 minus 9, and this just means negative. Yes, this just means negative. And and we also know that the last one had a spare room, like difference of 1. Here the difference is negative. So if instead we had, we will treat this as 10. Yes, let's treat this as 10. Yes, let's we can treat this as 10. 10 minus 9 is still 1. So we'll add 1 to our answer. Then we move on to the next number. And here we will treat this singular number as 11. And here we have 11 minus 9. Spare room of 2. We don't add anything to our answer. We already have our answer. 1 plus 1 answer should be for sixth 2, 1, 2, 3, 4, 5, 6, 2. Cool. I think we can do this. Mhm. And we have to find the grade. Where does this start? Mx equals 1, while mx is smaller, while mx into 10 is smaller than, let's say, r. Yep. Then we will do mx into 10. And we will get the the highest place, right? While true. Okay. And HL, highest digit in the left at the mx place would be L divided by mx, and highest right would be R divided by mx. And if HR greater, if okay, if HR greater than HL. Now, if HR minus H highest in left is greater than 1, then break, cool. Else, if not, then we have to see if HR minus HL equals to 1. Yeah. Then answer plus plus and mx divided by 10. Else, the only other thing could be that these two numbers are equal to each other, in which case we will have to increase the answer by 2. Answer plus equals 2. And any case, we will be moving to the next smallest digit. Then else, if that is not the case, then we will make HR multiply by 10. And if HR, we will do the same thing now. Set if HR was smaller than HL, we will do HR multiply by equals to 10. And we can use these same statements. Okay. And we only break when the spare room is too much. Okay, and sometimes we do not break. Okay, cool. Correct answer, even 18 and 12. Okay, cool. That shit. Okay, and this actually feels pretty good, solving a question in like 10 minutes, 12 minutes. and getting the correct answer in the first try, that actually feels a bit good. So you are solving, yes, random 15. Yes, I saw you were giving virtual contest. So no, stalking. This is not a stalking. This is like more seeing what your enemy is doing, and enemy in a like better sense than literally I want to kill you. Not like that. Enemy in the sense, let's grow together. Yeah, yeah. I was unable to solve C, but I did read the editorial and then I did solve C, and I that does not look good. Yeah, C did happen, but this, okay, we messed up somewhere in the theory. Okay, uh, mx, if I think if we were to take these as strings, this would be a bit easier. Taking this long max, we don't even need max int n equals L dot psi while n, mhm, we don't even need, mm, yeah, string makes like a lot more sense. If we will compare like the character which has the highest thing with the at the highest place value first in both the strings L and R. If L, the highest character currently in I is smaller than the highest character and the left number, yes. Okay, and we are going to do some crazy character mathematics, ASCII mathematics here. Yes, we'll just add 10 to this number, and yes, this is going to work. Now, if Ri minus the highest character minus in R minus the highest character in L is greater than 1, then just break. If the current highest character in R is like there is a lot of spare room, then we can just break. I think, and that would be very nice. Yeah. And otherwise, if we will have to see now Ri, or let's say int diff equals Ri minus Li, and here diff greater than 1, then this, if diff equals to 1, exactly equal to 1, then we can choose one of the characters and answer plus plus. Else, there is now only one possibility that the difference is equal to 0, in which case answer plus equals to. Okay, we messed up quite a lot in this one. If these two numbers are same, then don't do this. Only do this. In this case, yo, and here we got wrong answer for third last. Let's see that third last. Here 7744 same. So yes, answer increases by 4 at least. And then 5. I think we can break after there is a difference of 1. Okay. If I have 1, 2, 1 like 2, 2, we can still break. Yes. Okay, now something else is broken. This one. Here, everything till this point is same. But then the answer is messed up. Uh-huh. Depends on the next number. Set. So you cannot specifically break 2019. Here the difference is 1 for this digit, and we cannot just break it. Either we go with 19 or we go with 20, right? So we cannot break just yet, right? And is this the only case? If we had two, yes, the next one is like as small as it can be, and this one is as big as this can be. And do the other numbers, if this was like 299, would this matter? Yes, they would only matter as long as these two numbers are 0 and 9, and we would be adding 1 and 1. If this was any higher than 1, then 0, and this was any lower, like, and this was like same as it is, then for this we could choose 0, and this will work. So whenever we see a difference of 1, we will keep moving forward while we are seeing 0 and 9, and we will keep adding 1. So answer plus plus for this current one, and I plus plus go to the next place, and while I lower than n, and r I equals 9, or 9 as in this, with like same L is equal to 0. Answer plus plus, and I plus plus. Please, last one. Last one is okay, 22 minutes. We added this, this, this. We added 3 numbers, right? Since these are same, these are also same, and in total these are five numbers. So answer increased by 10 because they are literally the same numbers. So we do not have any other choice. And shit, this is the number on the right. This is the number on the left. And did I mess up? Yes, I did mess up. The next one has to be 0. And this one has to be 9. Okay, cool. This is working. This is working and hopefully will work. Hello, I've started C++ and I am in class 12. I have thought to take admission in local private college. Is it right, or should I go to some another college? And do you also do web development? I've done some web development. And as do you, should you take admission in private college or go outside? I would say if you can, if you think you have the ability to learn things on your own, then it is all right. Or I would say it is even better to take admission in a local private college because you will get a lot more spare time if you are studying in a local private college. But if you think you would need help, or like if you think you need exposure and you need to get out, then I would say go outside and like outside meet some new people, go and live somewhere in the hostel, and that would be also pretty helpful. But if you think you can do things on your own, learn things on your own, and manage things on your own, then yeah, it is much better to take admission in a private college because you will get a lot more spare time in that way. I go to I have at least taken admission in a private college near my house, and it is working pretty fine for me till now. Or maybe not, depending on how this. Okay, okay, yes, it is working fine. Maybe not. Shit, shit, shit. It is okay. Yes, it is working fine for me, and you can decide for yourself. But it is AKTU. Mine also is AKTU affiliated, and for exposure, I have some relatives on it sector and some school seniors in IITs. Okay, that is nice. And by exposure, I mean, I found a friend in my own college and he knows a lot more things than I do. Like, I was very impressed when I first met him. And okay, I should not say this to him, but he is one of the reasons that I am like getting better at things. And that I would say meeting that good friend of mine has been better than getting into an IIT. I mean, I do not know the IIT experience, but I would take this instead of going into an IIT because meeting him has been one of the best things that can happen to me. And I would say if you have someone like that, then it is okay. Like does not matter where you are. If you have already found some people who are amazing for exposure, then it is okay. Then you can take admission wherever. Does not matter because you already have found your circle. Okay, one question down. You will do 6 at least. This should be kind of like white. That would be nice. 1, 2, 3, 4, 5. Yeah, we'll do 6 questions at least. Cool. One down. But this one did took 22 minutes. Yeah, shit. This took 25 minutes, by the way. Just saying. Wait, this would actually be cool if it were in like the other way around, but yeah, that is fine. Let's read the editorial for this one. And before reading, wait, this one doesn't even have tags. That is crazy. Yo, bro, deleted. Okay, I think message got deleted automatically. Maybe you sent a link. I don't know why links get deleted. automatically. Moderation activity is off. Wait, this was question number E? This was question number E. Shit, that is a long way. Okay, note that the number x will have the same length in decimal representation as the numbers L and R. Consider this example for, let's see, for this the answer would be these two numbers are same. Yeah, that is all that matters. Answer would be 4. For the number x to be in the range between L and R inclusive, it must be of length 5 and start with the digits 1, 2. In other words, the greatest common we could have actually, yeah, this is fine. R implementation is also better, is also fine. The idea is the same. They are calling it, like explicitly calling it out as prefix, but we were calling it as numbers with nothing in between. In other words, the greatest common prefix of numbers L and R will be the beginning of the number X. Yep. Now look at the digits following the greatest common prefix, which should we could also have thought in the sense like if we add, okay, after taking out the greatest common prefix, now that is fine, that's fine. Okay. Now look at, now let's next look at the digits following the greatest common prefix, which in this case is 3 and 5. If these digits differ by at least 2, we can choose a digit in between them, excluding the boundaries and then filling in the remaining digits, the remaining lower digits, such there are no common digits with the numbers L and R. In this case, the example, we can take the number x equals 12400. We choose the digit 4 between 3 and 5, and then we can choose the lower two digits arbitrarily. Arbitrarily does not matter. Let's choose them so that there are no common digits in the numbers L and R. In summary, if the digits after the greatest common prefix differ by at least 2, the answer will be equal to twice the common prefix. Twice the common prefix. Yep. Now let's consider this case. Here we have the prefix of 1 and 2, and also this number does not, this number 4 and 3 only differ by 1. There is no number in between them, so we will have to go with either 3 or 4. Again, we can conclude that the answer x will be of length 7 and starting with the digits 1, 2. But in this case, 3 digits, the digits after the greatest common prefix differ by 1, which means we need to choose one of them. Let's consider option 2 for them. And yeah, this is like basically the same thing that we have written. Let's see their implementation. They have also taken this as a string. We also have taken this as a string. If the numbers are same, then output twice into size. Pointer, we have a pointer, while pointer is lower in size and the numbers are equal to each other, pointer plus plus, right. Now if the next digit in the pointer is, and also here we are blindly subscripting L with the value PTR, and we know that PTR will not be outside L because here this loop will not exit, because this loop, while loop, will not exit because of this condition. We didn't even had to use this condition because we already checked here whether these two strings are equal or not, and here we do see here, so when we are here we do know that there is at least one digit which is not equal in PTR, and we will exit at that pointer, and then we are checking, and if the difference is more than 1, we output this pointer answer is a response to +1 for the current digit, and then we are looking for how many 9 and zeros there are. otherwise break, and response. Yes. Cool. That is basically what we did. And now we can move on to the next question. Reset this. With 25 minutes. This one, let's do in 20 minutes. Cool. Jellyfish hates maths. Shit. A in division A. Division A. Question A. Shit. Jellyfish hates maths. Yes, I've not done this before. Jellyfish hates maths, but she has to finish her homework. Jellyfish is given an array of n positive integers, a1 to an. She needs to do the following two steps operation until all the elements of A are equal to each other. Select two indices, left, right, not same. Replace AI, GI with GCD of A. Why do I feel like I have done this question? Now, Jellyfish asks you for the minimum number of operations required to achieve this goal. It can be proven that she can always achieve her goal. GCD of AI and AJ. It can be proven. It does not matter the order of the array. Okay. So we would take the numbers which would give us the like either if one exists, then that one is already there. If there is a one, then the answer is going to be the total number of numbers in the vector minus the number of ones. Here there are three ones and the length is 3. Answer would be 3. Answer is 3. Here there is no one. So first we have to get a 1. But how are we going to get a 1? What are the limitations? N is 5000. We can go n square. We can go n square. We have to find the smallest. Either there are 2 or 3 numbers which will give us a GCD of 1. Okay, if there is no one, then we have to create a 1 and we have to find. Okay, shit. Either we find the smallest number of numbers for which we can take a GCD and their GCD will turn out to be 1. Either we do that or yes, we will have to do that. GCD 1, we have to make the here we just need to take GCD of these and these two numbers. Their GCD is 1. How can we fast forward this part? We have 5000 numbers. We can go n square if we want to, but in some cases, like in this case, the GCD of the combined numbers is going to be 1. GCD of this and this is 10. GCD of 10 and shit, not in this. GCD of 12 and 20 is 4. Yes, and we will make either this or this equal to 4. Right. How do we even get a 1 here? Then we take G. Should wait, answer is not possible here, I guess. In the first case, choose 3 and 2 and replace 3 with GCD this. So array becomes, here we get 10. And okay, we have to make them equal. Makes sense. We do not have to make them 1. We just have to make them equal. Okay, so we go through the whole thing. We find the total GCD. Yes, we find the total GCD. And yeah, so that GCD, whatever it is, that will be the number to which every number can be reduced to. Right. Here the total GCD of the whole thing is 1. So we will reduce all the numbers to 1. Here the total GCD is also 1. Here also the total GCD is 1, is 2. Here the GCD is 2 of the all the numbers. But how do we get a 2? Here we take GCD of this and this, we get 4 here, and then we take GCD of this and this, we get 2. Right. So we just have to figure out. So it took us 2 operations by taking GCD of this and this and then this and this, 2 extra operations to get a 2. And once we had a 2 here, we can take GCD of that 2 with this and this. Yeah. So yeah, first get the GCD number in the vector and answer would be total numbers minus 1. But if we already have it, then answer will be total numbers minus the count of the how many times the GCD is appearing. And yes, here we can make the GCD by doing just one operation. GCD of this and this gives us 1. Yes, GCD of this and this gives us 1. 2 numbers. So we did one operation to get a 1 here or here, does not matter. And once we had a 1, answer was 3 minus 1 plus 1. 1 plus 1 because of the extra operation we had to do. And that is crazy. Now all we have to figure out is how do we find out the minimum numbers which give us the smallest GCD, the minimum number of numbers, and the number of numbers for which we are taking the GCD, the number of extra operations would be the numbers minus 1. Here we have 2 numbers and we take their GCD, we get 1. Okay. And yes, every number would be divisible by their GCD. So as their factor, they would all have that number, and we can go n square. We can go n square. We can go n square. So would 2 numbers always suffice? Nope. Here the GCD was not present. Originally, we had to take GCD of the whole thing. Yeah. Let's say we do have the GCD. Yeah. Let's say we do. When we have this number, this has 2 factors. We have 12, 20, and 30. Let's say we have 12, 20, and 30. We can break down 12 as 2 into 2 into 3, 20 as 2 into 2 into 5, 30 as 2 into 3 into 5, and the GCD is 1. When we are taking GCD of these 2 numbers, you will get 2. Okay, and if we were to take GCD of this and this, you would get 2 and 5, 2 and 5, the common numbers. And when we take GCD of this and this, we will get 2 and 3, 2 and 3, because those are the common numbers. And let's say then we have, let's say 2 and 3 into a number. We want to remove this 2. How do we remove this 3? We take GCD with this. Okay. Yes. So if we have a number which is prime. The number of factors that a number has. If the GCD is not present already, then we need to make it. And yes, we do need to make the GCD, and we can do n square. And making a GCD just means removing factors, removing factors. For every number would have a number of factors. Here we had 6, 14, and 15. 6 has 2 into 3. 14 has 2 into 7. 15 has 3 into 5. We need to get to 1, and yes, every number also has 1, and also like themselves, but we don't consider that. 1. 1 into 1, right? How do we do this? GCD. We need to find the minimum number of numbers, which will give us this GCD. And I feel like I've done a similar question. But still, here, if you just take GCD of this and this, we get 1. That is one extra operation. And the answer would be total length 3 minus 1. Uh, 3 minus 1 plus the number of extra operations, which in this case is just 1. So answer is 3, which it is. We just have to figure out a way to find. Okay, do we actually need to find? We just need to find the least amount of operations it would require to get the GCD number in here. And this is question number A in division 1. Least amount of operations required to get a GCD of 1. And we can choose any numbers whatsoever. Yes, we can choose any number whatsoever. And the GCD, yes, I think it was a good idea to fall back at 1500. GCD has to be 1, 1, 1, or 1, or whatever the GCD of the whole thing is. What if we have 2, then we have 5, then we have 15, and here GCD was 2. Here, let's say 6. Here GCD was again 2, and here GCD becomes 1. So we see that this number is required. Uh, But also we don't have to take GCD of this whole thing. We can just take GCD of these two numbers, 2 and 15, and we will get a 1. And the answer would be 3 in this case also. Okay, the pair with the smallest GCD. Shit. But yeah, if you were going to do that, then this, okay, whatever the A value is, AI is also not very big. Okay, that might be helpful, might not be helpful. AI is not very big. Yes, we have reduced the problem, but we have the GCD of the whole thing. How do we figure out least the least amount of operations it would take to make that GCD? This is number theory. GCD, the least amount of operations it would require to bring forth the GCD. This kind of query is easy, but this and this. Say, maybe we can do some sort of, we can afford n square, and not just n square log n also. When we are at a number, in this case, when we are at 15, 15 has, maybe we can sort these or store these numbers as their factors. As in, we can store, like in the first test case, we have 12, 20, and 30. We can make an adjacency list representation, and we can write 2 into 2 into 3 as the factors. And also we can do this because, like, we will write the prime factors of number because a is not bigger than 5000. 12 is written as this, and 20 is written as 2 into 2 into 5, and 30 is written as 2 into 3 into 5. We have this, and let's say if we are including this number, what would be the least amount of numbers required? What I need is some number which does not have 5 as their factor, and a number which does not have 3 as their factor. And yes, numbers which does not have 2 as their factors, and numbers which does not have 3 as their factors. Here, this one does not have 5, does not have 5 as its factor, and this number does not have 3 as its factor. And we do not have both the things in the same number. We will have to use this, like all of these numbers, to get what we need. But there must be some other, like, better way to do this. Okay, we are already at the limit, and I think we can look at the editorial now, because yeah, it is fine. It is fine. There is no need to struggle. We can just look up what the right method is. We have thought about the problem, and yes, the only question that we need to know is how to find the um, smallest amount of numbers giving the least GCD, greatest common divisor. Okay, yeah, that is what we need. Yeah, that is what we need. And it is okay. It is okay to look at the editorial. It is not bad. Jellyfish, hint. Please think carefully about what happens after that. Jellyfish and flaming pony. This one. Try to think about why glucose travels achieve her goal, and ultimately what elements will turn into. The elements will turn into the GCD of the whole vector. When you have figured out, try using dynamic programming to reach your goal. Okay, question number A in division 1 uses dynamic programming. Shit, why didn't I thought about dynamic programming? Dynamic programming, we can think in terms of dynamic programming here. How would we define our state? We need to find a subset. Okay, we need to find a subset of the whole thing. Dynamic programming. Our question has turned into 12, 20, 30. But this has multiple choices. This doesn't even have one choice. This has multiple choices. Okay, at every number here we have a number, and here we have a choice to either go with this number. If we do go with this number, okay, then initially our GCD is equal to 30. If we do go with this number, and if we don't go with this number, then initially our GCD is 2, is 0. Right. And in this, our problem is reduced here, and initially we will say we have a GCD of 0 in one case, and we need to convert this using elements from this subarray to get a GCD equal to the total GCD, which in this case is 2. So how do we define our DPI state? Yeah, DPI, this will have two numbers. I think memorization would be much better here. DPI and like GCD, when we are here at, when we are only using from 0 till the ith array, and our current GCD is this. How many numbers do we have to involve to make this number into the total GCD, which we can define with like represent with capital G. And if we can never get to a GCD of capital G, then and our I equals like 0 or something, then answer is infinity or into max. And we can use recursion for this. And how will our DP depend? DPI and G equals either we do use this element or we do not use this element. If we do use this element, then answer depends on DPI minus 1 GCD of G and AI, ith element. This, or if we don't, then DPI minus 1 G. And also we have to take the, like the minimum of these two is going to be the answer. And recursion would be a much better approach. Wait, no, we can literally use a matrix because this value is not going to be greater than 5000 and this value is also not going to be greater than 5000. So that is n square. Yes, we can fill this iteratively and that would work. Let's fill this iteratively. Yep, we have a number. Okay, now also let's take the total GCD int capital G equals 0 for int x in a. G equals GCD of G comma x, the current number. If int CNT equals count in a dot begin and a dot n, how many times do we have G? And if CNT, like if we do have this some number of time, then answer is going to be this minus CNT, n minus CNT, and then return from this function. Otherwise, if that is not the case, if we do not have this, then we will have to make this. In that case, we will make a vector of vectors of integers. We will call it tab, and this will have n by 5000 elements, which we can write here explicitly. Range is 1e5 plus 1 just in case. Range and n plus 1, and let's say dp state db ix equals minimum number of elements required from the first I elements to make x equal to G. Okay, and we will initialize, we will fill vector int thing. We will fill this first column of tab 0 when we are not choosing anything, and whatever I here is, that would be equal to int max. Let's do that. Fill tab 0 dot begin and tab 0 dot end with int max. Okay, that is amazing. I equals 1, I less than equal to n, I plus plus. When we are using the first I numbers from our GCD, yeah, either we do choose this current number or we do not choose this current number. So tab I, when we are using the first I numbers, and for x equals 0, if we have a GCD of 0, yeah, do we want to go from 0? We do want to go from 0. Yes, we do go. When we do 0 represents we are not choosing the first number. Yeah, we are not choosing this current number. We just started from here. All right, and x less than range x plus plus tab I x equals minimum of tab I minus 1 x. In this case, we are not using this current I number, I minus 1, and GCD of AI I minus 1. G equals GCD of AI minus 1 comma x. G. And shit, not just that, we also need other base statements. How did you come to the conclusion that it utilizes DP? Can you recap how you came up with the DP states, the whole DP idea? Okay, I didn't know that this uses DP. I read the hint from the editorial. Here, hint number 2, when you have figured out hint number 1, try using dynamic programming, and this made certain sense. And yes, I'll just get into this first. Like, let me completely realize what this is. And if x is already here, x is the GCD, then we don't need to use anything. What if x already is the GCD? If x is the GCD, then we do not want to use this current number clearly, which would be reflected. If x is the GCD, then this we can, I think, when we are not using what if, hmm, okay, we have to reconsider what we are doing here. We have to kind of reconsider. The DP state, uh-huh, ing, this is correct. This is correct. But this part is wrong. Not wrong, but not completely right. Initial state has to be correct. Let's go with this. No, we cannot. Tab G equals 0. I think this is not enough. If we have, uh, yeah, if we have just a few numbers, 12, 20, and 30, and the target GCD is 2. Let's make the GCD table. Yep, when we are only using, and yes, this is going to have 4 columns when we are not using any number, when we are using the first number, when we only have this much array, first 2 numbers, when we have the whole complete first array, and this should have like 30 more columns, 30 columns in total, but we have a smaller representation of the same thing. And we have said when we are not using anything, then answer is infinite. But when we are here, this thing depends. Okay, and let's say this is 0. When we want to get to a 0, when we just started from this 1, 2, 3, and 4, and 5, and 6. Let's say yes, that is all we have. And yes, this is like OCD triggering. All of these are infinity, and DP I J, where I is row and J is column. This means when using the first I numbers from 0 till I, this much of the vector, and having a starting GCD of J, that is, we were able to achieve a GCD of J without using all of these numbers. How can we get to a GCD of capital G, which is the GCD of the whole array, with using as few numbers from this as possible? That is nice. And I think we should say if J is already equal to G, then this should be 0, right? Yeah, shit. Yes, that is all we need. So for in I, and we will do this for each row. I equals 0, I less than Ni plus plus, and not this less, equals. When we are using no numbers, or when we are using all the numbers, we will do tab I G equals 0. We don't need anything. We don't even have to do this. We can just say tab 0 G equals 0, and everything else is infinity. And yeah, this should work. And then let's see. See out ops, number of operations required, or number of shit. When you are using the current number, answer has to be this 1 plus 1 plus. Yes, 1 plus. Because in this choice, we are using the current number. So the cost of making the choice and the inherent cost of using the current number of operations would be tab n when we are using all the numbers and our beginning GCD is 0. That is, we do not begin with anyone with anything. So n minus OP, number of operations, n plus the number of operations minus 1. Okay, let's say okay, that is very close. I messed up with something. OP, OP minus 1, OP minus 1. Yes, OP minus 1. So totally minus 2, because if we are like using two numbers to get to the lowest GCD, then actually we are doing one operation. And in n, we had to do one operation, like n plus the number of operations, which is the number of numbers minus 1, and then minus 1 because we already have the GCD there. So this should work, and it does work. So that is nice. And now I can get into why this works, because that is the main thing. And 40 minutes are wait, shit, still this is not done, so we cannot stop. Memory limit exceed 5000 by 5000, 25 into 10 power 6. How much can we use? 25 into 10 power 6, 25 MBs. We should ideally be using 25 MBs. That makes sense. Let's not do this again and again, and say range, and make this a global phenomena, and this should work because there were multiple test cases. So yeah, and we were creating the same matrix again and again, but still that should also not be a problem. And let's see, I don't think that that should have been a problem. Memory limit exceeded on text 1 is crazy. Time limit exceeded. Range by range. Shit. Yes, of course, memory limit exceeded because this is not 5, this is 3. And we can put, yeah, and we can put this back here. This would work here, and this would also work like outside. Let's put this outside. Yo, hello. Flaming pony. Runtime error on test. Shit, because limits. It is 5000, not 1000. And that must be a boundary error, out of bounds error. Yes. Look at this memory usage. Yes, we went past test number 7, and that is nice. But it's also not nice. Ah, shit. Okay. Let's go through what happened. we take in n and we initialize a vector to take in the whole data. And now when we have the data, what do we need? In this question, we need to make all of the numbers equal to each other. And the only operation we can do is take one number and take its GCD with other number. And when you are taking GCD, the new number that you get is either equal to one of the numbers for which you took the GCD or smaller than them. The GCD is either going to be equal to the smaller number or smaller than that. So GCD is just going to decrease the numbers, not increase them. And the smallest GCD that you can get is going to be the smallest number, either the smallest number or this GCD of the whole array. So when you take GCD of the whole array, that is the number to which you are going to make the whole all of the numbers equal to. In this case, the GCD of the whole vector is 2. So you can make all the numbers equal to 2. So let's, and there can be now two scenarios after this. Let's say G denotes the GCD of the whole vector, and that is going to be the number. Hello, why are there less numbers of division 3 and 4 now? What do you mean? Number of contests. Why are there less division 3 and 4 contests? I don't know. 4, I've only seen one division 4 contest, and that is like they don't happen that often. I don't know why. Yeah, I guess people just don't make them. And I also think in division 3 and 4, it is more likely that the people cheat, and creating a contest is very difficult, and I do not think you would or anyone would want to create a contest in which a lot of people are cheating. And it is not as common for people to cheat in division 2 and not in division 1, certainly. I mean, no one, I don't think anyone would cheat in division 1 contests, because only people with a rating of 2000 can register in division 1. So I guess that might be the reason that they do not want to work hard for something in which people would just cheat anyway. Okay, so now we know that all of the numbers are going to be equal to the GCD. Now there can be two scenarios. Either you have the GCD itself as one of the numbers. If you do have it, then all of the other numbers which are not equal to the GCD AI, you just perform one operation with them and they will become equal to the GCD, because that is the definition. You take GCD with GCD, and this is the GCD of the whole array. This number divides every other number, and GCD is going to be equal to G. If it was like any smaller than G, then the GCD of the whole array is not equal to G. We are saying that the GCD is equal to G. So that is why this number divides everything. And this number might appear some number of times. And if it is appearing some number of times, since those numbers are already equal to the GCD, we don't have to change them. We only have to change the numbers which are not equal to the GCD. So the answer would be n, the total numbers, minus the number of times that the GCD is appearing, which we can say CG, count of G, if GCD is appearing in the vector. But if the GCD is not appearing in the vector, then we have to make it appear. And we would have to take GCD of some other numbers with this number, with this original number, let's call it. Originally, this number was EX, and we took GCD of this number with a few numbers, and we made this equal to G. And when this became equal to G, then we have CG, that is count of GCD, equal to 1. Answer here would be n minus CG, which is 1, n minus 1. But also all of these operations these extra operations which we performed to make this GCD come to life, and let's call it OP. So the final answer in the case when GCD is not in the original array, answer would be n minus 1 plus OP, number of operations to get the GCD. And when we have one GCD, the number of operations to make everything else equal to the GCD. And yes, that is the case. So now what we have to figure out, this case is easy when we already have the GCD. The answer is easy. After taking this, let's find the GCD. Int g equals 0. And we can initialize the GCD to be equal to 0 because GCD of 0 with any number is equal to that other number. And now we have to take GCD of 0 with of g with every other number for every x in A. G equals GCD of g and x. Now let's see how many times is this GCD appearing in the original vector. So count a dot begin and a dot end. What are we counting for? We are counting for g. If CNT is not 0, then it means we already have g in our original array, and our answer would be n minus CNT, which is the case for the second test case. Here the GCD is 1 and we already have 1, so that is the case. 2. Shit, that is new. Why did it even open? Okay, and yes, shit, that was not new, that was tmux script. Okay, now after this point, if we are on this line, we know that the GCD does not exist. We have to make the GCD appear, and now we have to use dynamic programming for this. And that is crazy. We have to define some DP state for each number. Let's say we have a couple of numbers, A1, A2, A3, A4, dot, till AN. What we need is the least number of numbers, the least amount of numbers that we can take, so that when we take their GCD, it is equal to capital G, the total GCD of the whole vector, and this count has to be smallest. We can define for each number we have a choice, either we include it or don't include it into our like this count, right? So let's define a DP state. So a DP state depends on what the current GCD is and how many numbers are we considering. So we can define our DP state as this: DPI and DPX. And we are saying when we are using the first I numbers, let's say I is some number, when we are using the first I numbers from our array and we already have the number X as the GCD, then this will be equal to the least amount of numbers required to get to the final GCD, which is capital G, right? So yes, this is how we are defining our state. Now, how do we define this recursively? In the recursive sense, this thing at here we have a choice either to include this ith number or not include this ith number. So if we do include this ith number, if we do include, then our state, this would depend. If we do include this, then answer would be dp I minus 1 for like, right, because this depends on if I is still here, then our substate or sub problem on which the answer for this thing depends on would be when we only have I minus 1 number of elements from the start, and our initial GCD, this x has changed because we are using the current number. And this x, instead of x, we will have, let's say, x prime, which would be equal to the GCD of x and the ith number, AI. So x prime, x dash or prime. And this thing would be how many numbers are required to get to GCD capital G when we have x prime and we are using I minus 1 numbers. And since we did use this current number to change this GCD, we would have to add 1 to this because we did use the current number. And other choice would be when we are not including this current number, in which case our answer would be dp I minus 1. Our state would still decrease, and the only change is this x, this current GCD would not change because we are not using the current number. And since we are not using the current number, we would not add 1 to whatever this thing returns. And the actual answer for this would be the minimum of these two things. That is dynamic programming. And now let's talk about the limitations. Here, I and x are the things which are defining our DP state. And here, okay, since there are like two approaches for dynamic programming, there is recursion, amazing spelling, and there is tabulation. And in this case, let's talk about the limits. I is the number of elements, and n, as we have seen, the limit is 5000. 5000 for n. So this thing on one dimension, our matrix, since our GCD DP is two-dimensional, we will have a matrix. On one dimension, it is 5000 integers long, and on the other dimension, it is also 5000 integers long, because AI is at max 5000. So x is also 5000. And if we were to use tabulation, we would have to fill a matrix of size 5000 by 5000, and that will take 2.5 into 10 power 6 amount of time, which is completely okay. We can do this. But if x was bigger, like 5 into 10 power 6, this much big, then we would prefer recursion. Why? There is a specific reason, because in this x, when we are using tabulation, we will be filling every single possible, we will be filling our answer for every single possible x that we could have, or also the x that we would never have. But using recursion, we would only solve the sub-problems which are required to be solved. So in this case, if x was big and I was also big, then using tabulation, we would be solving every possible subproblem. But if we were using recursion, we would only be solving subproblems which are required to be solved. And using recursion, we would be cutting down the number of subproblems that we are solving. And using tabulation, we would be solving a lot of subproblems, and that is a lot of work to do. And usually, when the amount of subproblems is same in recursion and in tabulation, then tabulation is faster because there is no function call in tabulation. There are just like one or two loops in tabulation, but recursion is slow because of function calls. But here, the slowness that comes because of function calls is like nothing compared to the fact that we are not even solving all of the subproblems using recursion. That would be good. But here we can afford to use tabulation. So that is good. So we will have a vector, we will call it dp. Size is going to be n plus 1, and on the other dimension we will have range, which is, let's 1 5e5 5e5 plus 1, just in case. And we will say, when we, for every dp 0, for every, like every x, when we are not using anything, answer is going to be infinity, except when x equals to g. When x equals to g, answer is 0. We do not need anything. When the GCD is already what it needs to be, then we do not need anything. So let's initialize this part. Not infinity, let's use n. N is much better than infinity, because in our dp state at this point we are adding 1 to another value, and if we are using int max, then adding 1 to int max will overflow. So that is something we should avoid. So instead we will use n. And why n works? Because if you are using all of the numbers available, then that is like the worst case. So n works. What we will do is fill dp 0 dot begin and dp 0 dot end with the value n, except when dp is 0 we already have g, then the answer is 0. Now we have to iterate for I equals 1, I less than equal to n, I plus plus, I meaning the number of numbers we are using from our integer, from our vector, and x equals 0, x less than equal to range. Just less than range would work, x plus plus. Now, and okay, let's say g is the GCD of the current number I minus 1. Here I is one indexed. Here we are starting from I. So we have to do I minus 1, because I in the vector A starts from 0. So current number and x. X is the GCD that we currently have, and AI is the current number. So dp, when we are using I numbers with, when we already have x, answer would be minimum of dp I minus 1 x. This is the case when we are not using the current number, and 1 plus dp I minus 1 g. This is the case when we are using the current number. And now our number of operations is going to be equal to dpn when we are using all of the numbers, and our initial GCD is 0 minus 1. This is giving us how many numbers, how many least amount of numbers were required to get to a GCD of capital G, this one, and the number of operations is going to be the number of numbers which we have used, the count of numbers, minus 1. And now we can apply our formula which we wrote, n minus 1 plus off, C out, n minus 1 plus off. That does work. Shit, I got afraid for a second. That might not work. Wait, why are there like 2 test cases now? Should, by mistake, I created a new test case using some key. Shit. Using some key, I created a new test case, which is shit. How do we create a new test case? Okay, I will look it up after the stream, but that is nice. Yeah, that is how you do GCP, like dynamic programming. Yeah, cool. So one more question done. but this one took 44 minutes, which is not very good. We'll do 6 in total. And yep, 2 questions done. Second one took about 45 minutes. Second one is not good. Okay, but yeah, it just tells how much difference there is. This was question number 1 in Division A contest. Now, this one, hacking. That is big. That is a big thing. This is an interactive problem. Okay, we will do this now. And before proceeding, I would like to go to the washroom and I will be right back in a minute. I'll be right back. Yo, I am back, and if like something didn't make sense, please feel free to ask. Okay, some frames were dropped, but that is fine. Now the next question, which is an interactive problem. Yes, let's go. And okay, we will since this is an interactive problem, we could go with printf, scanf, or we could go with streams, C in, C out, IO streams, or standard input output. We will implement this in both the ways. Yeah, that would be nice. Yeah, drink water just after coming from the washroom. This is an interactive problem. Welcome. Timer has started. Welcome. Duelists. In this interactive challenge, there is an unknown integer. You must make it equal to a integer. You must make it equal to a given integer in the input n by har- harshening the power of match mech monsters. You can send a command to do one of the following. These are the commands: add y, constraint this y can be this, result is this, if result is this, then x becomes equal to that, if not then x remains 1, and if x did change then we will get 1, and if we were outside this limit then we get 0. Okay, and multiply x by this, and same thing, or divide if y divides x then this, otherwise no. Okay, digit gives the number of digits. Sn is the function that returns the sum of the individual digits of a non-negative number. Okay, you can make up using at most 7 commands. N is the number that is given to us. X is something that we do not know. Okay, Okay, 7. 7. We will have n. We have n, that is the number to which we have to make the number x equal to. We do not know x. Do we need to know x? If we can if we can make x equal to 1, and then we can just multiply 1 by the given number n, then we could be able to do this. Yes, that is one approach. How can we make x equal to 1? If that is the case, then we will have to make x, whatever the number is, integer x, equal to 1 in 6 moves. And I don't know how we could use this operation. Okay, this could also be wrong, but I think that would be nice to make x equal to 1, and then we can multiply x by n and make x equal to n in one operation. But before that, we have to make this. So, wait, we cannot minus. Shit, we cannot subtract. So, how do we decrease x? The only way to decrease x is dividing x by some number. We can keep dividing x by some number. And let's rewrite this question and say we need to figure out what x is. And the only input that we get is this 0 or 1, 0 or 1, telling us if the operation was successful or not. Telling us if the operation was successful or not. And n is also an integer. This is the only response that we get, whether the current operation was successful or not. And if you want to increase x, there is multiply, add. Those are the only ways to increase x, and division is the only way to decrease x. And we would not want to do both of these operations, like multiplying x by some number and then dividing by some other number, because we could do that in a single operation. Yeah, if the GCD of this y and this y is 1, then it would make sense. Otherwise, no. And this is the only operation we can use to decrease x. Yo, what do you think? We can decrease x. Okay. And also, is it like all? I don't think it would always be possible. Shit, it is possible. If we do know x, what x is, if we can figure out x, we can divide x by itself by giving in x, and then we can multiply x by the target number n to make it equal to n. So two operations just gone in that case, and we would have to figure out what x is in 5 moves. in 5 commands at most. And two, because 2 commands, if we do know what x is, 2 commands would be taken in to make x equal to n if it already is not equal to n. So we have like made use of this case, this, but we don't know how we can use this. Fair. No, no, no. 10 power 9 is a big number. 10 power 9 is a big number. That is like 2 power 32. And initially we have no idea what x is. Wait a minute. The amount of operations is just not a lot. Here, we do have this operation. And using this, we can yeah, we can figure out if the current number is divisible by 3 or not, and also 9 or not, but that does not help us a lot. If what we get after this digit operation, if that number is divisible by 3, then x is also divisible by 3. Okay, so we know one factor, but if it is not divisible by 3, then what? Then we cannot do anything. No, wait. 7 operations. Using this, let's say for example, x equal to 9 and we had to make it equal to 100. Let's take that case. X was equal to 9 and we had to make it equal to 100. If we do the digit operation, we will get 9. And what information does it give us? We only know that the sum of the numbers is equal to 9 and the number is divisible by 9. And that is all we know. That is literally all we know. Can there be some other information? Nope, 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 nothing else, nothing else. Multiply 10, multiply 10. These are the only 4 operations we have. Add, multiply, and division is the only thing we can use to reduce the number. And this operation must also be helpful in some case. If we use the digit operation, and let's say we see that the current number is divisible by 9, right? And then we use the, okay, and when we use the digit operation and we do see that we get, and then we again, whenever we use the digit operation, and if we get 1 as the answer, then it might mean that x equals 1 or 10 or 100 or anything. If you have a number like 9 and we need to make it equal to 10, we need to make it equal to some, if we have a number x and we need to make it equal to some other number n, then we have to do x y into n, and we can reduce this fraction. We can take the GCD of these two numbers and divide these by 2. We do know this number. We don't know this number. We just need to figure this out. And yes, once we know what x is equal to, we just need two extra operations to make x equal to n. But before that, we have to know what x is. We do 0. We do add minus 10. We cannot add minus 10. So we do add 1 and we multiply by 10. Yeah, we have the answer here. Digit. We ask for the digit. We see 1. We divide by 2. And we get the answer. But we get 10. Then we divide by 2. Yeah, x becomes equal to this. So that is a whole different thing. That is completely different. Shit. We can make x equal to the sum of its digits. We can make x equal to the sum of its digits, and that is pretty nice. So this is also one operation we can use to reduce x. But if x is a single digit number, then nothing would happen. And yeah, this operation like always works. What is the biggest value that x could be equal to? Let's say all the 9 digits are equal to 9. So x would be equal to 81 in that case. And yes, that is the maximum value this could have. And then we do 8 plus 1. Or what is the biggest two digit number we could have? 8. Can we have 79 here? Yeah, 79 digits. Yes, we can have 79. And then we do the digit operation again. Then we will have another two-digit operation, two-digit number. And then we will have a one-digit number. Right. So that making x a one-digit number took how many operations? 1, and then to this 2, and then to this 3. So in 3 operations we can make x out of 7, 3 operations, we can make x equal to a one-digit number. Now, when x is a one-digit number, we have 4 operations left, and x could be equal to 1, 2, 3, 4, 5, 6, 7, 8, and 9. When x is equal to a one-digit number, we have 4 operations left, and yes, we can figure out if x is... So half of these numbers are even. That is one thing, and also have some primes in here. Prime, 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 prime. And we have even numbers, and we have numbers divisible by 3. 3, 3. Mm, Shit, or okay, y cannot be equal to 0. I thought we could just multiply x by 0 and then add 1 to x. And yes, that would be magical, but no, shit. Wait, okay, if we add some magical number like 9 or 10 to this, you'll get 2. If we get 10 to add 10 to this, we will get 12. And if we do the digit operation, we'll get 3. If we add 10, we get 4 and 5 and 6. Nothing. Yeah, that doesn't help. If we add 9, here we'll get 1. Here, this will become 11 and we'll get 2. Here we'll get 3. No, doesn't help. So there has to be something else. We can now multiply, add, divide. For divide, if we do divide, then we can know among the 4 operations left. Yeah, let's say we will, after knowing what x is equal to, we'll need 2 operations to make x equal to n. So let's say we have 2 operations to determine in, in this range 1 to 9 what x is equal to. And using one operation, which is division, we will be able to know if x is even or odd. And then if x is even or odd, if x is even, then either, now the number that we have is either 1, 2, 3, or 4. This would be our search if x is even, or if x is odd, then our target x could be equal to 1, 3, 5, 7, and 9. And why, if x is even, uh, x could only be equal to 1, 2, 3, 4, because if x is even, then it would be divided by 2 and its value would change to that even number divided by 2, which are 8 divided by 2, 4, 6 divided by 2, 3, 4 by 2, 2, and 2 by 2, 1. So if we do go with the division by 2 number, then our search space reduces to 1, 2, 3, 4 if x is even, and if x is odd, then 1, 3, 5, 7, 9. And now in one operation, we have to figure out what x is equal to. Okay, If we again, like actually speaking, we have three operations left. If we again divide x by 2, in this case, if we divide again x by 2, if we are at this or this, if the current number is even, then we would have x equal to 1 or 2. And then we have just two operations left. Now that is crazy. That is crazy. That is crazy. That is crazy. Okay. At the 30-minute mark, we will look at the editorial. Till then, we will think. Do we actually need that many operations? Okay. Since what is the maximum value that x can have? X can be equal to 10 power 9, which is like 1 with 9 zeros. 10 power 9 and yes, 10 power 9. But if we have a number like 10 power 9 and we use the like digit operation, since there are 9 nines, sum would become equal to 81. If we do the digit operation again, sum would become in this case 9, a two-digit number. But we could also make the sum equal to 79 with changing the last 9 equal to a 7. So the sum becomes 79 and now if we do the digit operation, we get 16, and now if we do the digit operation, we get 7, one digit number after doing three operations. One operation to get here, one operation number 1 to get here, operation number 2 to get here, and operation number 3 to get here. And after doing three operations out of the total of 7, we know that currently x is a one digit number. We have four operations left, and x is a one digit number from 1 to 9 range. We have to figure out which number x is equal to in this range. In this range, which number x is equal to, and how do we figure that out? We have just four operations left, and not just figure out, we also have to make x equal to n. We have just four operations left. Okay, let's use three of them to make x equal to 1, and then one operation to just multiply x by a number. Yeah. So now to reduce x, all we can do is use the division operation. And what is the liberty we have? We can use this operation 3 times. That is the maximum amount of times we can do this operation. 3 times. We can do this operation three number of times at max to make x equal to 1. And we have and x possibly could be any of these numbers. And we do know that x is equal to any one of these numbers, and we have three operations to make any of these numbers equal to 1. If we use the division by 2, if we divide x by 2, if x, now there are two cases, if x actually is divisible by 2, any of the even numbers, then we will know, we will know, and we will have one case, 2, 3, 4. This would be our new space, and if x is not divisible by 2, x would not change, and our new space would be this. New search space would be this. Now, if x was divisible by 2, then these are the numbers we have, and we have two operations left at this stage. Two operations to make these. We do know for a fact at this point that x is one of these numbers, and to make these numbers divisible by 2, if we divide again by 2, let's say if we do divide again by 2, either whatever the x is, if it is divisible by 2, then we get 1 and 2. If it was not, then we have 1 and 3. We have reduced the search space, but now we only have one operation, and we need to make x equal to 1. Okay, we can just divide x in this case by 2, and in this case by 3. If x was already equal to 1, it will remain 1. If x was not equal to 1, then it will become 1. Here we can divide x by 3, and if x was equal to 1, then 1. Otherwise not. Cool. Cool. Shit. Okay. So here, if x was a even number, then we are able to get what we want. Now, here we have how many? Two operations left. Crazy shit. And among these are the only possibilities. Here, let's say we divide by 3. If we divide by 3, if it is, if x is divisible by 3, then what we have is 1 or 3, and in this case, we just divide by 3. If x was not divisible by 3, then we have 1, 5, and 7, and we only have one operation left. But we cannot work with this. We cannot work with this. In one operation, we cannot deal with this. Is just too much possibility. 5 and 7 is just too much possibility. If we just had one more operation, everything would be cool. If we just had one more operation, everything would be cool. Because, yes, if we just had, do we have one more operation? Initially, we did the digit operation. How many times? In total, we have 7 operations. We did the digit operation 3 times. So we had 4 operations left. And among those 4, we can only use 3 operations here. And yes, when we do one operation on this list, we arrive at this possibility. Now we only have 2 operations left. And if x is divisible by 3, then we can make x equal to 3, x equal to 1. But if x is not divisible by 3, then either we have 5 or 7. 1 works. 1 is like amazing. But 5 and 7, how do we handle the case of 5 and 7? If we just had one more operation, everything would be happy. Everything would be cool. But we don't. Yo, bro, shit. It gets boring. Uh, okay. Maybe we do not. Yeah, we do have to do all of these 3 operations, digits. The maximum value that x could begin with is 10 power 9, which has 9 digits. Like this has 10 digits, but the maximum value would be when every digit is equal to 9, and we can have 9 digits equal to 9. Sum is 81, but we can turn one of these 9s equal to 7, and the total sum would be 81 minus 1, 79, in which case we do the digit thing again. If we do the digit operation again, we will get 16. So once we did the digit operation and we got a 2-digit number, yes, that is guaranteed. We will get a 2-digit number if we do the digit operation once. We are guaranteed to have a 2-digit number if we do the digit operation once. Yes, and then on that 2-digit number, if we do the digit operation, we might get another 2-digit number. Then we will have to do the digit operation once. Okay, what is the biggest value this other 2-digit number could have? That is a nice question. What is the biggest value that this other 16 is actually the biggest value that this other 2-digit number could have? Because to get to 16, we want to maximize both of these numbers. And in one place, 7 here is the highest and 9 is the highest we could have in our answer. So 16 is the biggest 2-digit number that we could have after performing the digit operation at least 2 times. And okay, so we are guaranteed to have 60 or some number, bro. So we are guaranteed to have a 2-digit number less than or equal to 16. Okay, after 2 operations. Let's work with this range. We have the possibility is to have a number from 1 to 16. 1, 2, 3, 4. Let's use like actual numbers. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is the whole possibility of numbers that we could have. And if we do the and how many operations do we have left? We have in total 5 operations left, and we will save one operation for multiplication in the end. So we have 4 operations left. 4 operations left at this stage. And now if we divide by 2, and if the number is divisible by 2, then we have one case, and otherwise we have another case, and we are dividing by 2. If the number is divisible by 2, then the possibilities could range from 1, 2, 3, 4, 5, 6, 7, 8. The biggest even number we have is 16. And if the number is not divisible by 2, then we have possibility 1, 3, 5, 7, 9, 11, 13, 15. Not divisible by 2 and divisible by 2. Okay, so what do we do in this case? And we have 3 operations left. Okay, we have 3 operations left. If we divide by 2, here we have 1, 2, 3, 4 even numbers. We will reduce like our search space to 4 numbers. Let's say we again divide by 2. Here we will have 1, 2, 3, 4. If the number was divisible by 2, but if not, then 1, 3, 5, 7. And we have 2 operations left. All right. Shit. We cannot do this. We cannot do this. We cannot do this because here all of these numbers are prime and we would have to at least divide by two of them to make the number equal to 1. And if our number is not divisible by any of these, we have wasted our two operations and we are stuck with whatever the number actually currently is. And we might not be able to make it equal to n, because let's say if x equals 7, but our target is 15, we cannot multiply 7 by any number to make it equal to 15. That is, yep, we cannot do that. Let's look at the editorial now. That is fine. That is fine. We can look at the editorial. This is, let's see. C1, hacking numbers, and it is fine to look at the editorial of numbers, of questions. Yeah, it is fine. It is fine, right? Yeah, I think it is fine. It is fine. It is fine. It is fine. Figure out a way to make x equal to. That is what we have been trying to do. Then finally, add n minus. We can add n minus 1. We don't specifically have to multiply. Shit, we have the answer. We had the answer before this shit. In this case also. No, 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 no. Here, yeah, I guess this is a better choice. Yeah, this is a better choice. Here, when we are here, we will divide x by 2 again. And if x is divisible by 2, then we will get 1 or 2. And we have only one operation left. Then we will divide x by 2 again. If x is divisible, then x is equal to 1. If x is not divisible by 2, we will have 1 still. So x is equal to 1 in both of these cases. And yeah, and we can add n minus 1. And here, if x was not divisible by 2, we would have 1 or 3. Then we divide x by 3. If x is divisible by 3, we will have 1. If not, then also answer, we would still have 1. Here we divided by 2, here we divided by 3. And here we divide by 3, let's say. If divisible by 3, then we have 1. If not divisible by 3, then we have 1, 5 or 7, and we have two operations left. One operation left. We have one operation left. That is crazy. We have one operation left. Okay, when we do have a two-digit number, one-digit number, 1, 2, 3, 4, 5, 6, 7, 8, 9. We multiply by 2. Multiply the number by 2. This number by 2. If you multiply all of these numbers by 2, we will get 2, 6, 8, 2, 6, 8, 10, 12, 14, 16, and 18. And if we do the digit operation, then our possibilities are 2, 6, 8, 1, 3, 5, 7, and 9. We basically got all the numbers back. Shit. Yes, we did got all the numbers. We'll also have 4. That doesn't help. We have all the numbers back. Let's, yeah, look at the tutorial. And that says how many more operations or more questions we have to do. What range of values can x take of first x can be equal to after the first digit operation from 1, or wait, what is the initial value? Initial x can be 1, yes, from 1 to 81. What about the second digit operation command? If we do the second, then the range is from 1 to 16. Avoid overusing digit command after the second application. 1 to 16, consider using the binary representation of x instead. So my phone is going to die, not the laptop. That makes sense. So we do not have to move forward after 16. What do you mean consider the binary representation? His phone is charging, that is pretty nice. When x is equal to 16, after doing the 2-digit operations, x is in the range from 1 to 16 plus 16, and we can represent this by 0 0 0 1 2 4 8 16. Avoid overusing the digit operation and avoid overusing digit command, and after the second application x is limited in the range, yes, consider using binary representation of x instead. Okay, x can be a lot of numbers in this range. Our range is 1 to 16, and binary representation 4 0 0 0 1 0 0 0 1 0 1 1 0 1 0 0 0 0 1 0 1 0 1 1 0 0 1 1 1 1 and 0 0. Let's half numbers are here and half the numbers are here. 0 0 1. But do we need what can we do with this binary representation? Wait, yeah, I didn't miss a number. That is nice. Yes. After this 1 0 0 0. That is the biggest value x can have. Now we have make binary representation. How does the binary representation of x help when we are in this range? X could have possibly, okay, x cannot be equal to 0. That is like a non-possibility. X could be equal to any of these things. X could be equal to any of these things. And if X is equal to one of these things, how can we make X equal to 0? We have to figure it out. And the operations we have are add, divide, digit, and multiply. I don't think we will use multiply. We might. How would the binary representation help? And at this point, out of the 7 operations, we have used 2 operations. We have 5 operations left. Shit. Shit. All we need to know is the information about these 4 bits. If we do know the information about these 4 bits, we do know the actual final value. How do we check if this bit is on or off? We can check this by dividing x by 2. If we can divide x by 2, we can only divide x by 2 in half of these cases. This, 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 this. Right, the last bit is now gone. And yes, if we now if we do again, now we will divide x. If the number was divisible by 2, that would be one case. Okay, and how would we know if this bit is on or off? By binary representation. How can we know a number like, yeah, let's say 15. 15, let's say we get that the current number is not divisible by 2. That tells us that the last bit is on. And if the current number, okay, let's cut that off. If the current number is divisible by 2, then we know that that originally last bit was off, and now it got replaced and the whole number got right shifted by 1. And if it was not, then we know that the last digit is 1. If it was divisible by 2, we will divide it again by 2. And if it was not divisible by 2, we need to know this bit. And when is this bit on? This bit is on in 3, and in other representations, yeah, we will divide by 3. We will divide by 3 if the number is divisible by 3. Then let's say a number like 6. Well, shit, 6 is divisible by 3, but in the binary representation, wait, no. 6 is 110. 4 plus 2, 6. Yeah, shit. 6 is an even number. So yeah, we don't have 6. We don't have to think about 6. Can we know the last bit? Okay, we do know the last bit in both of these cases. Originally, x was equal to 0. Here, x, the last bit is 1. How do you know this bit? And the next number that is divisible by 3 is 9. That would come when we add 3 to this. When we add 1, we get 1, 1, 1. We add 1 more, we get 1, 0, 0. We add 1 more, we get 1, 0, 0, 1. Which is like 1 plus, yeah, shit. 1 plus 1. 8 plus 1, that is 9. 0, 2, 4, 8. 8 plus 1, 9. And this is also divisible by 3. So, yeah, this does not tell us anything about this bit. How can we gain information about this bit? We do know that the LSP is 1. If we add, we can subtract 1. And we do have a number that is divisible by 2. Okay, let's look at the answer. Yeah, it has been 55 minutes. That is a long time. Apply digit. Yes, that is the range. That is the second range. Apply minus. Wait, x. Shit. That was actually stupid. If we have numbers from 1 to 16, shit. That was only a consequence of not reading the problem statement correctly. If we do minus 8, if the number is actually in the range minus 8, from 2 to 9, then it will become from range 1 to 8, and from range 1 to 8, the number would not change, but then from range 9 to 16, the number would become and come in the range 1 to 8. So if we do minus 8, wait, minus, we can do minus. We cannot do minus operation or add minus 8. We can do minus. Y can be negative. We can do minus. Add minus 8. Shit. If we do minus 8, we get a number in the range 1 to 8. If we do minus 4, we reduce the range again by 2. 1 to 4. Minus 4. So, uh, 2 operations done to get to this range. One more, 3 operations, 4 operations in total to get to this range, 3 to get to this range, and now minus 2, add minus 2 from 1 to 2, 5 operations to get to this range, and now minus 2 and 6 operations to get to 1. Shit, and then just multiply by n. Shit, shit, shit. That was crazy. That was crazy. We can do this now. We do know what is. Okay, let's first do and then we will reflect where we messed up. Uh, yes, let's use the C in syntax. This false is okay. We can remove this and things will be happy. Then, yeah, then what is the syntax? Add some number and digit, digit, digit. So, C out digit, new line, digit, new line, flush. Okay, and then see out, and also like yeah, this would return two numbers. We don't even need to know those numbers. Wait, can we do this? Shit, that is crazy. Wait, shit, let's go all out with this. And after two digits, we'll do add -8, new line, add -4, new line, add -2, new line. And we have here performed 1, 2, 3, 4, 5 operations. -8 and the range became 1 to 8, then -4 range became 1 to 4, -2 range became 1 to 2, and then we did -2 again, right? -2. Wait, digit, digit, -8, -4. So digit, digit, two operations to get to here, three to get to here by -8, and -4 here to get to this place. Shit, yes, three operations to get here, four to get here, five to get here, and when we were here, we do -2 again. Yeah, so we have to do -2, add -2, backslash new line, and we have done like 6 operations. So taken 6 times, 4 times, 3, 4, 5, 6. This is crazy. 1, 2, 3, 4, 5, 6. And I expect this to work. And then see out, add, and -1. Flush. And then yes, we have to take in number. C in, C again. Or we don't actually have to take in the number. We can, after this, a new line, and bingo, bingo, and new line. And flush and C in C. Let's, we have two operations. Make n is 100. Okay, okay. Yes. So let's just give random input. 1, 1, 1, 1, 1. Add 99, and we are here. Shit. This might work. This might not work because the input and output buffers are different. So I think this might work. This might not work. We will have to see. Yeah, this does not work. We do have to go through like the correct way. See out, running the loop. See out, digit, new line, CNC, taken again, and now we will do like see out, add -8, new line, C in C, and yes, the same thing. 8 changes to 4, then to 2, and then again to 2. After this, C out, add n minus 1, new line, and then C out. Bingo. And you might notice that there is no end line or flush. I think that will work because I remove the line cin dot tie with null pointer. I think that should be okay. That should work. That should be like, yeah, because that should cause, whenever we are calling the cin operation, that should cause automatic cout flush, hopefully, or maybe not. Okay, not. Let's use end line here. And what is the error? Is the error because of okay, let's start a macro. Press Q, F, Fn, A, minus minus, go to the end, remove this, end line, L, this, and then exit enter mode, go down, down again, go to the start of the line, and stop the macro. And now you will see some magic. Shit, okay, you will see some magic. 3 at the rate F. That was magical. And at the rate F. Even, yeah. So the new line got replaced by end line. Like slash n got replaced by end line. That is cool, except in this case, because here the format was a bit different. And this should work, hopefully. No, it doesn't work. Nope. What is the problem then? Interaction in n C out, end line does have internal flushing. Add space mul div digit digit case sensitive. These are case sensitive. Add minus n, add 1 mul, and then bingo. Let's use printf and scanf. Yeah, scanf a digit percent tt, get the number of test cases here, while tt minus minus. Wait, there are multiple test cases, right? Yep, two test cases. While tt minus minus and n can f percent d get into n. Yes, and after getting n, you will do printf some printfing, and that would be first perform the divide operation, twice, flush standard out twice, do this thing twice, flush. I don't have. Also, after flushing, a digit c. Okay, and then subtract minus printf, add a digit, which in this case is minus 8, and then scanf this, also flush std out tool. Okay. Here, whenever I'm printing the lines that I copied earlier, the cursor stays at the start of the new print statement of the new lines that were printed, but that is bad. Think in Vim how to put the cursor in on the printed lines. Nah, to the end of the last line. No, no, no. Shit. There was a like a specific command that I read about. I guess it was GP. Yes, GP 4 2 2. And how many operations have we done? We did one operation here, two operations here, four operations, two operations, three operations, four operations, five, six, and as to the last operation, after taking C, we will do the last operation. Print F, add a digit, and that digit is n minus 1. And yeah, flush xtd out and scan F, take in T, and yeah, printf after that. Bingo. Yeah, that's it. That should work. Yeah, that should work. I mean, I don't know why the earlier version was also not working. That is crazy. We were using flush and we were using, yeah, we were using everything that we should, but still it was not working. And compiler error is great. That makes sense. That makes sense. Is it compile? T is compiling. No compilation error. Wrong answer on test case 1. That is crazy. That is actually crazy. Let me go to the washroom and I will be right back. And wrong answer on test case 1 is crazy. Cool. I'm back and we got a wrong answer on test case 1. Why our number was equal to expected 5 found 1. Input. Each test case contains T and first and only line contains n integer. N was this and X was this. Output 100. We did make 100. Expected 5 found 1 for 1 2 3 4. Okay, let's say there is one test case and the number is, we want to make it equal to 5. All right, digit. So our initial number was 1 2 3 4, and if we add 1 2 3 4 we get 10. So our number became 10. So we did do the digit operation. Okay, and let's say 1. Yeah, cool. And then we do the digit operation again on 10. Okay, we will, our number becomes equal to 1. That is nice. Let's say 1 minus 8 from 1, 0, minus 8 minus 4 from 1, 0, minus 2 from 1, 0, we cannot do that, minus 2 from 1, 0, we cannot do that, add 4 to 1, if we add 4 to 1 we get this. Why didn't this work? Expected 5 found 2. And this is also like, all right, this is also non-adaptive. When you have determined that x is equal to n, output a line in the following format. This, when the jury will output a1 if n is equal to x, otherwise manifold. Shit, okay, we have to read another number after this, after outputting this. Scanf %d, Thomas C. Yeah, cool. This should work. Yeah, shit. That was the only mistake. We were not reading the input. That does not make sense. Expected this, found this. 1, 2, 3, 4, 5, 6. Wrong answer. Final value of x is not equal to this. Test case 4. That should not be the case. Scan integer into n. Do the digit operation once, twice, and also read the C, the output of those operations, then -8, then read the output, then -4, again read the output. When we did -8, the range reduced to 1 to 8. When we did -4, the range reduced to 1 to 4. When we did -2, range reduced to -2, from 1 to 2. And when we did -2 for the last time, now we do know that the number is equal to 1 at this point, and we have done 1, 2, 3, 4, 5, 6, 6 operations. And as the last operation, we do this, add n minus 1, or we could say multiply by n. That also works. Flush, scan, print, flush, scan. Print, flush, scan. That is the case. Print, flush, scan. Then the next operation, print, flush, and scan. And also in the last thing, print, flush, scan. Why didn't this work? That is like crazy. Nothing is working here. Test case 4 again. This is our x value and this is our target value, and expected this but found this, found this, which is twice this number. So x was not equal to 2. X was not equal to 1 in the last case. Okay, and so x was not equal to 1. Why was x not equal to 1? We did the digit operation twice. We did the digit operation twice. So this should work for this specific x also. 629. X was 629. We did the digit operation 8 plus 9, 17. Do the digit operation again. 8, cool. Then minus 8 does not work on this. Minus 4 does work, we get 4. Minus 4 does not work. Minus 2 does work. Minus 1. Shit, shit. I just messed up a lot in this question. Okay, and now this should work. And after this, we will do the whole implementation again with standard, uh, with streams. Yes, that is working. That is working with the streams C in and C out streams. Yes, let's do the whole implementation again correctly this time. Remove this and int n, C in n. And what was that line even doing? This line. This line is a crazy line. This line is telling by default, when we do not have this line, whenever we do C in, by default, whatever we did C out, whatever string we did C out, it gets C out flushed by default. This thing happens. This thing happens by default whenever we call this, and then we get our value into our variable. But if we have cin dot time null pointer, then whenever you call this, this thing does not happen. So that is nice. But here we do want our output to be flushed out to the screen, but we do not want it generally to happen because we might be getting like big arrays in input, and whenever we are calling, like we would be in that case calling this operation 10 to the power 6 times, and we do not want to call the flush operation 10 to the power 6 times because this is slow. So normally we do not want this to happen, but here we do want this flush to happen. So let's remove this line. Yeah, and we now don't even have to use flush. N N C in N, and now C out digit new line, and then we take in the input, or for int I equals 0, I less than n, I less than 2, I plus plus. As like seasoned programmers, we do this. Right, and after doing the digit operation twice, we'll do int some variable x equals 8 while x greater than 0, C out, add space minus x, and in line, and yep, and then C in into C and C, and then x left shifted, right shifted by 1. Cool. And then bingo. And this should also work. Would this work? Yes, this should work. This would be cool. This would be cool. This should work. Let's see. Or maybe this might not work. Shit. Why is this not working? Okay. We did the digit operation twice, and then we did add minus 8, right? And then, yes, int c, taken c. And then in the next iteration, x was divided by 1, so x became equal to 4. Then we did add minus 4, then we did add minus 2, then we did add minus 1, and yes, After that, we have to do add n minus 1, new line, and C, taking C. Yes, shit. Yes, that was kind of obvious. Shit. Okay, now, hopefully, or if you might some compilation error. Now there should be fixed, and this should work. Yeah, this should work. This should work. Yeah, and that is nice. And let's see if I add that line back, the int die null pointer, then this will fail. Then this will fail because the output is not getting flushed. I will get error that program sat idle for a long time without any output. Then this will fail. Then this will fail. And the only change is this line. See, it is like still running. It keeps on running. And yep. Let me turn on the fan for a minute. I'll be right back. Wait a minute. Yeah, idleness time limit exceeded. Yo, yep, idle limit exceeded because of that single line. And if we do want to include that line, then and yeah, did you like see that? That was pretty cool. If we do want to include this line, then whenever we are doing cout, we have to accompany that with a flush operation. And shit, now we have something amazing Vim features which we can flex. In this line, we will do the global command with where every line where we have a cout. Yes, every line. On that line, what do we want to do? Shit, we want to go to the end of the line and do some macro. Yeah, shit. No, we cannot do this. We have to manually do end line here. Digit, end line here, end line, end line, end line, and this will work now because end line has flush operation associated with it. Should I forgot to stop the stopwatch? Yep, it is working now because of the end line. And yeah, we were unable to do this, or I was unable to do this quicker because I didn't read the problem statement correctly. The fact that rs only increases if it is positive. So x can never become negative. And also we can add negative numbers. Yeah, shit, that was bad. Now let's move on to the next question. There was a list of questions here. We have done 3 and they are taking increasingly greater amount of time. We have done 3 questions. Let's do this one took like 1 hour and 20 minutes. Now on to another next question. Refresh, reset. But I guess that just means I do not deserve my current rating, which is 1400, because I'm struggling with these questions. Yeah. News escape. This would be the next question, and let's do this. And wait, how long has it been? It has been 3 hours already. So, okay. Neo wants to escape from the matrix in front of. Wait, why do I feel like I've done this question? There are n buttons arranged in a row. Each button has a weight given by an integer. Neo is immobilized, but he can create and move clones. This means he can perform an unlimited number of actions of the following types, two types in any order. Create a clone in front of a specific button, move an existing clone to a position left or right. In front of him are n buttons arranged in a row. Each button has a weight given by an integer. Create a clone or move a clone in front of a specific button or move a clone to the left or right position. As soon as a clone is in front of a button that has not been pressed, regardless of whether he was created or moved, he immediately presses it. The button has already been pressed and a clone does nothing. Buttons can only be pressed once. For Neo to escape, he needs to press all the buttons in an order that the sequence of the weights is in increasing order. That is, if this are the weights, then okay, your task is to determine the minimum number of clones Neo needs to create in order to press all the buttons in a valid order, and this is the order. Okay, so how many numbers are already in an ascending order? Here answer would be 2. Here answer is 1. Here answer is 1, 2, 4, 1, 2, 3, 3, 3. Answer here, wait, 2. In sequence, this. Non-increasing, okay, descending order. Again, the same mistake. So we must begin with this number, okay, 9, and next, the number that we need to press. Okay, if the number is like, okay, we will have a bunch of numbers which we can have, and then from we will sort the array, and we will also have the original array, and we will start our process by placing a pointer here. Yes, the greatest number, biggest number, and a pointer to the left and the right of that number, because we can increase those, we can press those buttons whenever we want. And the next button we have to press would be the next smallest number, which is 8. And if that number is not at the horizon, then we create another bot and place our pointer there, right? And then the next button that we have to print is 7, that we have to press is 7. We can press it, that is at the horizon. And the next that we have to press is 5. We can press it, it is right here. The next one, 2, we can press it. Sorry, the next one is 1, and we can press it here. 10, 10, and 10, and these are separated with a 2, so that does not help. And then we need to press this 7, this 9, and this 9 is separated by smaller numbers. Okay, and then we need to press this Seven is only separated by big numbers. That is nice. And 1 and 2, these are only separated by big numbers. That is nice. So we had to create a clone here and here for pressing 10, and then we had to create a clone here, and all the other numbers only had bigger numbers in between them. That is nice. So we have to go pairwise, and we have to see if the numbers between them, between the current pair, if there is any number that is bigger, that is smaller than the current number, then shit. Yes, okay. We can do this. We can do this. Boilerplate and take in n, and then vector a n for reference x in a, c in x, take in x, and after taking all the numbers, we okay, how do we would like to quickly I think we can use a map here, map which has a vector associated with itself. Mhm. Yep, a map which has a vector, but then no. Whenever big numbers have a smaller number in between them, whenever the next index of a number has a smaller number between them, then yeah, then we have to create a clone. If you were to make a graph out of this thing, 1 7 9 7 1 10 uh, 2 10 10 7, we need 1 2 3 clones, because there are 3 peaks. Yeah, because there are 3 peaks, we need 3 clones. How can we figure out where the peaks are? Or we just need to know how many peaks there are. Wait, shit, we just have to look at the numbers on the side of this number. Here, the next number is bigger than this, so cool. And on the left, there is no number, so yeah. Here, the next two numbers are messed up, so we will have to create one thing, one block for this. And then for this, we have a bigger number, so cool, nothing. We don't have to add anything. For this, both the numbers are big, so no worries. For this, both the numbers are small, so +1. And then for this, both the numbers on both the sides are bigger than this, so no worries. Here, this one is small, but we have a number that is equal, so no worries. Here, also. Hmm. Hmm. Yeah, we want to treat this as one thing. So yeah. That is very normal. Okay. Answer equals 0, and we will start for int L equals 1. R also equals 1. R is smaller than N. L equals R. And for the first number, if A 0, wait, and also answer is like minimal. Yeah, answer will start from 0. And at least how many numbers are there? At least n can be equal to 1. Right. So after taking if n equals 1, C out 1, new line, return. So here we do know that n is at least like 2. And if the first number is bigger than the second number, then answer plus plus. And now, while r is smaller than n and a l equals a r, then r plus plus. Now r is the next number, right? And we always have a number on the left. So if r is smaller than n, now if if r is smaller than n, then we will see. And also let's not go there. For the last number, we will find out the answer separately. We will look at it separately. Yeah, we will for the last number, we will look at it separately. If r is smaller than n, then we can access r. So if a l minus 1 is smaller than a l, and the right number is also smaller than a l, which is a l is bigger than a r. In that case, answer increases by 1. But if we cannot access, if r is like out of the bounds, then we cannot access r, and we will only look at the left element. If al minus 1 is smaller than al, then answer plus plus c out answer, and wrong. Here we say 0, even though that does make sense. That does make sense. Okay, so this is because we are handling some cases separately, and this should not happen. Okay, ideally this should not happen, and we should start from 0. No, let's start from 1. Let's start from 1. Let's start from 1, and answer would at least be equal to 1. If n greater than 1, if n greater than 1, then do this. Otherwise, do nothing. And here, output maximum of answer or 1. That is strange. Maximum of answer or 1. So answer in the first case came out to be 0. You can look at the element on the left. If the element on the left is smaller, which it would be, yes, when we are at 5, so answer increases by 1. And answer should also increase for the initial 4. Greater than 1. Yeah, cool. Cool. This should work. This should work. And we can submit this. But before submitting, let's rewrite int n. We take in the integer n, and then we have our vector a of size n, and then we are taking in on the all the numbers. Now we are filling in the vector, and initially let's say answer equals 0. Now if n is greater than 1, we will handle the first number separately. If a if a2 a1, that is the second number we have, if that number is smaller than the first number, then answer plus plus. And what we are just checking for is if the neighbors of a number, both of the neighbors of a number are smaller than the number, then we increase our answer there by once. But if the neighbors are not great or not smaller, at least one of them is either equal to the number or greater than the number, then we do not increase the answer by 1, because we already have we will have someone or some like bot who will increase that, who will be there to press that button. So we do not have to care for ourselves. For a smaller button, we do not have to care if there is a button to either left or right. For this, on the right, this button will be pressed before pressing this, so this does not require a clone. But this one cannot be pressed by anyone, so this has to get a clone for itself. And L equals 0, and this syntax this trick, as you might, L equals R is a, like, I guess, pretty cool trick to find out ranges in our vector. While R is smaller than N and A R equals A L R plus 1. And yeah, we will have L pointing to the current number and R pointing to the next number that is not equal to the current number. So if R is smaller than N, then there is a right neighbor, and we will check if AR, that right neighbor, is smaller than AL, the current number, and AL minus 1, the left neighbor, is also smaller than AL. In that case, answer plus plus. Else, if R is like out of the range, then we only have a left neighbor and a L minus 1. If that left neighbor is smaller than the current number, then also answer plus plus. And now see out. maximum of one or answer. Why maximum? Because in some cases, answer might just remain zero, and we do not want that. So yeah, and answer is always at least equal to one. We at least need one bot. So yeah, that is also nice. Okay. We have at least one button. If we have more than one buttons, then we are handling the keys for the first button. If the value of the first button is greater than the value of the next button, then do this. Let's say we have one test case with five numbers, and we have five, four, three, two. Answer should be one. Answer is one. And if we have a test case, one test case, five numbers, one, two, three, four. Answer is one. That is amazing. That is what we want. Simply one test case, five numbers, one, two, three, four, five. Everything is in order. Yes. If the right neighbor is smaller and the left neighbor is also smaller, then increment the answer. If the right neighbor is smaller and the left neighbor is smaller, then increment the answer. And if there is no right neighbor, there is only the left neighbor and the left neighbor is smaller, then also increment the answer. One test case with seven numbers, one, two, three, four, one, five. We have used seven numbers, right? Three, one, five. Answer is two, which is correct. Two is correct. So why is this wrong? That is kind of crazy. I do not want to look at the test case, which gave the wrong answer. If ans non-increasing, so either equal or smaller. Equal or smaller. He immediately presses the button. We don't need to press. Shit, this is literally what shit in the graph definition also. When we were thinking about this in terms of graph, this is what we are looking for. The peaks. How many peaks do we have? Here, one peak, and a peak only exists if the left neighbor is smaller and the right neighbor is also smaller. Left neighbor is smaller, right neighbor is smaller, left neighbor is smaller, and right is also smaller, or one of the neighbors does not exist. We are looking for the peaks in here because we can only go from top to bottom at every peak. If we start from here, this bot can only press all of these buttons at maximum. This bot can only press all of these buttons at maximum, and this bot here can press all of these buttons at maximum. And this bot cannot jump. What if we had something like this, a smaller peak? That would still work because this bot here on this hill cannot go up from here. Yeah, no one can go up. So we have to create a one new bot here who will, yeah, go down. R plus plus R is not pointing to the correct thing. Yeah, let's look at the test case. Left value, right value is smaller and left value is smaller. Only then increase answer. If the right value does not exist, if we are at the edge, what if? One test case, 5 numbers, 1, 1, 2, 3, 4, 4, 4, 4. Answer is 1, which is correct. Okay. Uh, we have one test case, 7 numbers, 1, 1, 1, 4, 1, 1, 1. Answer is 1, which is correct, which is correct, which is correct. Let's do, we have one test case, 8 numbers, 4, 4, 1, slope. That makes so much sense. That makes so much sense. Okay. I see the mistake. That makes so much sense. R equals 0, and while R is smaller than N, and AL equals AR, R plus plus. If R is smaller than N, and shit, which is like literally the same thing here. So we can start this from 0, and after getting L and R, if R is within the range, oh, that is like well and okay. If L, then we do this. Else, if not L, then we only have the right number to compare with. And if the right number is smaller than the left number, then answer plus plus. Here we know that we do not have a right number, so we might at least have the left number. We might at least have the left number. So if L, we might or might not have. If L, then we can normally do this. Else answer plus plus. This would just mean, yeah, we don't have left or right any number at all. And we don't even have to do that. Cool. And this will work now. Yep, this should work now. And it has been 3 hours and 50 minutes. 5-0. This does work. And 30 minutes. Not very good, but fine. We have done 4 questions, and that is, let's say, okay. Okay. Tomorrow we will aim for 6 questions. 4 questions is not acceptable, but okay. We should not haste, and we can increase this over time. We can like make this better over time. 30 minutes. So yeah, if we sum this thing, That is about 3 hours. And 3 hours to do 4 questions. But the stream has lasted 3 hours and 50 minutes. So yeah, 50 minutes, you're just like not even doing anything. That is crazy. That was nice. 4 questions done. And in the last question, the mistake was that we were not initializing these variables correctly. That was the mistake. And let's see, did they come to the same conclusion as us? Tags, what are the tags? I suppose that the tags are going to be two pointers, two pointers constructor algorithm. No two pointer, greedy is there. That is nice. Let's go to the editorial. This is called C news escape, C in division 2. That is nice. Note that the consecutive buttons with the same weight do not affect the result, so we'll keep only one of them in such sequences. Yeah, we were messing up our answer because of that. And in the resulting array, we see peaks, local maxima. Right. That is like literally what we did. We were looking for peaks. We also made the graph analogy. In the resulting array, we find peaks, local maxima, elements that are strictly greater than both of their neighbors. The number of such peaks is the answer because each peak is separated from others by smaller elements. Therefore, the only way to reach a peak is by creating a clone there. If a button is visited, we can return to it. Yeah. Any element other than a peak can be reached from a higher neighbor since we have visited it. Thus, creating clones in all the other elements is not necessary. Time complexity O of n. And how do they handle this? Push initial. Okay, that is very nice. That is very nice. And also push back a very small number at the end. That is very nice actually. And okay, okay, if the last number is not equal to x, if the last number is equal to x, then do not push it. If the last number is different, then do this. And we can go from 1 to size of a minus 1. That makes so much sense. Okay, cool. So they created a buffer so that they do not have to go through this all of this if else statement, and that is actually pretty smart. Let's copy that. We'll not we'll say what the size is. A dot, or we can say actually what the size is, and that is int minimum value that a integer can have. Now, I less than n I plus plus take into C if uh, a dot back the last element in a is not equal to C, then a dot push back C, and at the end a dot push back in min. We have a nice buffer here, and answer equals 0 for int I equals 1, I less than a dot size minus 1 I plus plus. If both the elements to the left and right of a are smaller than it, ai is greater than ai minus 1, and ai ai is also greater than ai plus 1. Then we do answer plus plus. See out answer. And will this work? Yes, it will. Cool. Submit. the better version of the code, and hope it does work. It does work. That is nice. That is nice. Cool. That does work. That is nice. And that would be it for today's stream. And if among the two people who are watching, if there is like something you want to see, now would be the time. And I would be ending the stream now. We have done 4 questions. Yeah. Let's see if we would be able to do 5 tomorrow. And then yeah, we will take it up to 6. And so I guess that is it for today. Thank you for being here.